Well, hi friends. This is a screencast that begins a discussion on what's called limits. We begin the discussion by taking a look at rates of change, by taking a look at tangent lines, two topics that might be familiar if you've studied physics before, specifically kinematics. If you've had any experience with pre-calculus, you have probably studied an idea like this before. So let's start at the very beginning. So let's imagine, if we can, that the height of a ball at some time t is given by h equals 490 minus 4.9 t squared. This assumes a couple of things. It assumes that we drop the ball. Oh, that's terribly sloppy. So sorry. We're going to assume that we drop the ball from a height of 490 meters, and we're going to assume that time is in seconds. That's how that 4.9 becomes possible. And there's some decimal places afterward, but it's good enough for now. So 490 minus 4.9 t squared. This graph shows how the height of the ball changes over time. That is not the actual path of the ball necessarily, but it is a graph that gives us the height of the ball over time. We assume that gravity is the only actor upon the ball. It's in free fall, a pretty standard pre-calculus type example. So what happens now? Well, we figure out some things about the ball, like when does the ball hit the ground? Well, if I want to know when the ball hits the ground, I have to know where the ground is. The ground is where the height is 0. Well, the height is the vertical axis, so I want to know where the height is 0. This is where height is 0, so that's got to be right there. Now, if I don't know what that is, if I don't want to count tick marks and figure out where that is, I could know that height is 0, so height is 0. And it should be easy to solve from there. That's not too bad. And it seems reasonable if you're dropping a ball from very, very high up that it might take 10 seconds to fall to the ground. Then you might ask a question like, how fast is the ball moving? And that becomes an interesting question because how fast it's moving changes. You're used to problems where we say a car is driving at 50 miles an hour and it's always driving at 50 miles an hour. Even if in a 30 zone, it's always driving at 50 miles an hour. But when we say how fast is the ball moving, you know that as the ball gets closer to the ground, it moves faster and faster and faster. So when we say how fast is the ball moving, that sort of depends on where we're looking. So let's change the question. What is the ball's average speed for the first 6 seconds? If we were to compare the starting time to wherever time equals 6 is, if we were to look at the average speed, what would the average speed be? Well, the average speed is the slope of what we call a secant line. It's a line that hits the curve twice in some small interval, looking for the slope of that line. So I would be looking for the height at 6 minus the height at 0 over 6 minus 0. And I happen to know what those are. That's 313.6 minus 490 over 6 minus 0. And that's negative 29.4 meters per second. Now, mind you, negative 29.4, that's a velocity, not a speed. Speed has to be positive. So to answer the question technically, honestly, we would say that the speed is 29.4 meters per second. Why is there a negative there? Because we're heading down. So if you want to pause for a moment just to make sure that you have some sort of understanding, you could find the average speed over the first 10 seconds. You would do a process very similar to the one I just did. You would find the slope of the secant line between the red dot and the initial dot. Okay, if you hit the pause button, then you now realize that the average speed on 0 to 10 is 49 meters per second. The average velocity is negative 49 meters per second because the ball is heading down. But usually, folks, we're not interested in what the average speed of the ball is. I want to know exactly how fast the ball is going at 6 seconds. I want to know exactly how fast that ball is going. And if I want to know exactly how fast that ball is going, I want the instantaneous speed at time equals 6. The instantaneous speed. And to get an instantaneous speed, I have to draw not a secant line, but what we call in the business a tangent line. A line that ever so gently kisses the curve just once. There. That line ever so gently kisses the curve once. I want the slope of that line. That is a tangent line. Now, what's the problem with that? When I go to find slope of a tangent line, I do the change in y over the change in x. So I would look for a rise and a run, and I only have 1 point. So if I only have 1 point, there is no change in y, there is no change in x. So consider the following. Consider a very small interval around 6. Let's consider the interval from 6 to 6.1. And let's do the height at 6.1 minus the height of 6 over 6.1 minus 6. This is the change in height. This is the change in time. Let's look at it in a very small interval, because then I could say that the slope between 6 and 6.1 is pretty much the slope of the tangent line. And if I did that and cranked it all out, I would get an average velocity of 59.29 meters per second. 59.29. And you say, well, that's pretty good. That's a pretty good approximation, but we can do better. Let's look at the subinterval from 6 to 6.01. Again, 6.01 would put you really, really close to the red dot, and you would imagine that the slope between 6 and 6.01 would be really close to the slope of the tangent line. And so we would figure out the height at 6.01 using our graphing calculator, minus the height at 6 over 6.01 minus 6. Change in y, change in x, change in height over change in time. And if we crank all that out, we would get negative 58.849 meters per second, which would be a better approximation of the instantaneous velocity, but it's not exactly the instantaneous velocity. So we choose a smaller subinterval, and we say, well, this has got to get us really, really, really close. And sure enough, it does. And this average velocity is negative 58.8049 meters per second. Now, we could take smaller and smaller and smaller subintervals, and we would find that the instantaneous speed gets closer and closer to negative 58.8 meters per second. But we would have to take smaller and smaller intervals and kind of see where the numbers are going to lead us that way. Well, I wonder if we can get a little more formal. I wonder if we can say, what if I want the instantaneous speed at time equals 10, the time it hits the ground? Can we get more formal? And the answer is yes. We're going to take the average speed on some interval that starts at 10 and ends at 10 plus h, where h is going to represent a very teeny tiny quantity. we're going to take an average speed on that subinterval. And then what we're going to do is we're going to let h get really, really small. We're going to let h get really, really close to 0, so that if you imagine this is 10 and this is 10 plus h, we're going to take this point and slowly drag it so that the two become one in a beautiful ceremony surrounded by family and friends. So what I'm going to do is I'm going to figure out what the height is at 10 plus h, and then what the height is at 10, and divide by h. And when I do that, here's what I get. I get 490 minus 4.9 times that input squared, minus, well, I know where the ball is at 10 seconds. At 10 seconds, the ball is on the ground. And I divide by h. And if I do a whole lot of algebra that you would have to hit the pause button and do on your own, if I do a whole lot of algebra, this thing simplifies to minus 4.9h minus 98. And this, in fact, tells us if I go from 10 to 10.2, then I plug a 0.2 in here, and that's my average speed on the subinterval. If I go from 10 to 10.001, then I sub in 0.001, and that gives me the average speed on that very small subinterval. But what I really want is I want the instantaneous speed. And the instantaneous speed is what happens as h gets closer and closer to 0. And the closer h gets to 0, the closer this gets to 0, and the closer the whole thing gets to negative 98 meters per second. Which means that as the ball hits the ground, its speed is 98 meters per second, and it's traveling down. So there's a second video that'll be a part of this lesson that will talk about slopes of tangents to other functions if you need to see some other examples. Otherwise, this will do just fine. You want to come in to class knowing average rate of change, instantaneous rate of change. All right, thanks.